Hi, welcome to another video. On this session, we're going to talk about something called exact differential equations. First of all, we're going to discover how in the world they solve the exact differential of a two-variable function. Let's assume that we got a two-variable function like this, so the exact differential of this function would be equal to partial f derivative with respect to x dx plus partial f derivative with respect to y dy. And you definitely consider on this fact that partial derivative with respect to y is not equal to dy, so that carries the concept of partial derivative. Let's start off with a two-variable function which is equal to a constant function, so the differentiation of f is equal to 0. And we can write this process down as the exact equation equal to partial f derivative with respect to x dx plus partial f derivative with respect to y dy and equal to 0. I'm going to go ahead and find the equation actually due to the exact differential. We got an equation written in this form. M is a two-variable function produced to dx plus n as a two-variable function multiplied in dy, and it is all equal to 0. This equation will be called the exact differential if it conforms with this description. So by equating m, which is the coefficient of x, with partial f derivative with respect to x, and also by equating n, as it is the coefficient of dy, partial f derivative with respect to y, we're going to get a function perhaps like f, and as I told you, it will be equal to a constant value. But the point is how to realize that the differential equation is an exact equation. If we can prove that a differential equation written like this is an exact equation, by the way, we can derive the coefficient m with respect to y, and also we can evaluate the n coefficient with respect to dx. Here you see they are equal to each other, so we approach to this fact that they are exact equations. Pay attention on this fact that the derivative we take of these functions are cross-sectional. I definitely mean you take the derivative of x with respect to y and vice versa, take the derivative of y with respect to x. Before keeping on this process, I want to take a look on integral constant values. So the idea for single variable functions similar to y equal to f of x, the constant value of the integral would be a definite value. Better to say we have constants, and the reason is the action of derivating of these functions. And if you take the derivative of x squared plus c, you'll find out that the derivative of a constant value will be 0. What about two or multiply variable functions? The integration constant is considered as a function of variable which we did not integrate it. To put it simply, we're going to consider on the integral of xy dx that we got f of x and y as a two-variable function equal to a constant value. By evaluating this integral, we'll have y times the integral of x dx, and the integral is multiplied to y, so the answer would be y x squared and half plus constant value of integral, which is importantly the function of a variable that we do not integrate it. This is g of y, so because the integral we have evaluated is with respect to x. And obviously you know what the reason is. If you take the partial derivative of this function, we will have g of y, which is not the dependent function to x, and that would be equal to 0. Here we have this function. Let's carry on to get the point of exact equation with it. I've just given the details about exact differential, so you actually remember that the partial f derivative with respect to x that we've called the coefficient of dx would be equal to m. That is the coefficient of the exact differential equation. By cross-multiplying, we'll approach to df equal to m of x and y dx. By integrating of both sides of this equation, we'll finally have the function f. And here we have f equal to the integral of m of x and y dx plus the constant value of the integral, g of y. After writing this equation, we have to find g of y because it is the unknown function. To find the value or the equation of g of y, we're going to use another property of differentiation method. So the partial f derivative with respect to y is equal to n. By differentiating f of x and y with respect to y, I wrote the derivative for u, and I eventually put it equal to n. So the derivative of g of y would be g prime of y. And I write the equation in which n is equal to the derivative of f with respect to y. So we can get g prime of y. If I take the integral of g prime of y, I'll get g of y. We want to examine this solution, so I've got an example for you. You're asked to solve this equation y over x plus 6x dx plus ln x minus 2 dy equal to 0. The first and mostly important step is to check whether this function is exact differential equation or not. In this equation, we got the coefficient of dx equal to y over x plus 6x, and here we have the coefficient of dy equal to ln x minus 2. Then I take the derivative of n with respect to y, and I take the derivative of n as dy coefficient with respect to x. So here we got y over x, and the derivative of this function with respect to y would be 1 over x, and 6x would be 0. Where the derivative of n with respect to x, that would be 1 over x minus 0. And these are exact equations under these conditions. If m is partial equation with respect to y, and if n is partial equation with respect to x, then these should be equal to one another. In other words, this is an exact equation. So let me tell you how to solve it. Here I wrote the exact differential formula. I just have to get partial f with respect to x where it is m. By cross multiplying, we approach to df equal to m as a function of x and y. Therefore f would be the integral of m of x and y dx plus g of x. But let's say I just integrate m with respect to x, and I got m equal to y over x plus 6x. By integrating, I got y over x. It would be y times ln x, and the integral quantity of 6x would be 3x squared. I told you about g of y, the constant integral value that I don't take integral from. This constant value called g of y that can be easily evaluated by putting n equal to partial f with respect to y, so I take the derivative of f function where df is equal to n. So we got y ln x, the derivative with respect to y would be ln x, and the derivative of 3x2 with respect to y would be obviously 0. And the derivative of g of y would be g prime of y. So here we have partial f with respect to y, it is equal to n function of x and y, and I can solve g prime of y. I got n equation here, ln x minus 2. Both sides of this equation is equal to one another, so I can omit ln x. I would have g prime of y equal to negative 2. By integrating with respect to y, the integral of g prime of y would be g of y, and the integral of minus 2 would be negative 2y plus c, the constant value. The only thing you are obliged to do is to plug g of y quantity in the f function. Then f of x and y would be y ln x plus 3x squared minus 2y equal to constant quantity. Quickly to show you another example, we are asked to solve this equation. I use the same exact differential way to solve it. I will take derivative of dx coefficient, m, with respect to y. Partial m with respect to y is the derivative of this product equation. It would be the derivative of the first function multiplied to the second function. Here we have the derivative of these functions equal to 2y times e to the xy squared plus the derivative of the second function multiplied to the first function, and the derivative of e to the xy squared would be 2xy times e to the xy squared, and eventually I multiply it to x squared. In addition, the derivative of 4x cubed with respect to y will be 0. On the other hand, I would evaluate dy coefficient's derivative with respect to x, and we call this coefficient the n function. Partial n with respect to x is equal to the derivative of this equation with respect to x. And again, I'm about to evaluate derivative of a product. Here we have the derivative of the first function multiplied to the second function plus the derivative of the second function multiplied to the first function. By doing all kind of stuff, we will have this equation. And certainly, partial n with respect to y is equal to partial n with respect to x. Conclusively, it is considered as an exact differential equation. Due to exact differential equation rules, the coefficient of dx would be m, so partial f with respect to x is m function of x and y, and we can get df, which is equal to m of x and y dx, and the f function would be the integral of m of x and y dx plus g of y as a constant value. By plugging the m quantity that is equal to this equation, we can solve this and get f of x. So we have to find the integral of this equation. It would be the integral of y squared e to the xy squared plus 4x cubed dx. It is equal to y squared times e to the xy squared over y squared plus the integral of 4x cubed, and that would be x to 4 plus g of x, the constant value. Next, we're going to evaluate this constant function. So I would take derivative of f with respect to y and put it equal to n. By deriving f of x and y with respect to y, we'll have the derivative of e to the xy squared equal to 2xy e to the xy squared. And the derivative of x to 4 would be 0. Finally, the derivative of g of y would be g prime of y. 2xy e to the xy squared plus g prime of y would be equal to the function we have just called n. I solved the equation, so it would be 2xy times e to the xy squared minus 3y squared. By omitting some parts, we will have g prime of y. And the final step is to integrate this g prime of y function, so I would have g of y itself. The integral of g prime of y is equal to g of y, and the integral of negative 3y squared is equal to negative y cubed plus constant value. I just plugged g of y in the f function formula to get the equation. So here we have f of x and y, which is equal to e to the xy squared plus x to 4 minus y cubed equal to c. I hope you enjoyed this video. Thank you for following us.